In this video, we're going to look at solving equations, dealing with either exponential functions or logarithm functions. And we can basically break these into four types of problems. For the exponential functions, you can either have an exponential equals a number or an exponential equals another exponential. Same thing logarithmic. You can either have a logarithm equals a number or a logarithm equals a logarithm. Basically, in all of these cases, we're going to deal with the inverses. So with the exponentials, we're going to take a log, or it's going to say instead of take, I'm going to say use the log. For the logarithmic equations, we're going to use the exponential. Again, that's the purpose of the inverse function, to undo it. When we have an exponential equals a number, generally we can just switch forms. If I have an x and an exponent, a power equals a number, I can switch it to logarithmic form, and it's pretty easy to solve. Likewise, if I'm in logarithmic form, I have a logarithm equals a number. If we just have it that, we're in our basic logarithmic form. Don't know what to do? Switch forms. Change it into a exponential function. And so, when we have an exponential equals an exponential, we have two cases. If I have the same base, I can use the fact that these functions are one-to-one. So, same output means the same input. So, I can just take advantage of the fact that if I have something to a power equals the same number to a different power, the two exponents are equal. And that's pretty easy to solve. We did that back in the exponential part of the chapter. If I have a different basis, I'm going to take the log of both sides. I need a little more room to work right here. With logarithm equals a logarithm, it's pretty much the same thing. If we have the same base, we come back and we do what we did up here. Again, a logarithm is a one-to-one function, so same output means the same input. If we have different bases, we're going to have to do the same thing. Use an exponential on both sides. Now, the good news for us is the examples that we're working on right now, we're not going to really deal with this case at all. We're going to focus on same base solving logarithm problems. And if they're different bases, use a change of base formula. Then that might help you. Might not, but it's an idea. Exponential, we will take advantage of this fact of using a logarithm to do both sides and work with that. So I'm going to go through some examples of these different types of problems with you. We'll start with this problem, an example of an exponential equals a number. When we look at this, we have one exponential function. So to get exponential equals a number, I got to get rid of the 3. So I'm going to start by dividing both sides by 3. I get 1.25 to the x minus 7 equals 8. And now I have my exponent equals a number. I've gone as far as I can go, so I'm going to switch this over to logarithmic form. So I'm going to rewrite this as the log base 8 sorry, undo that. The log base 1.25 of 8 equals x minus 7. But now this is pretty easy to work with, because I can do that with the change of base formula. The log base 1.25 of 8. I'm going to make that the log of 8 common log using common log. Calculator does that. Log of 8 divided by 1.25. And I'm going to get 9.3189, plugging into my calculator, equals x minus 7. So I add 7 to both sides, and I will get 16.3189 equals x. Now, anytime we solve an equation, we do need to plug this in and check. So please take a minute to pause the video, plug in 16.3189 into x in this equation. But if you do that, you should find out that that's going to equal just slightly over 24. It's 24.00 something on there. Again, this is an estimation right there, so that gets us a good estimated answer. So let's go to another example. In this case, I have an exponential equals an exponential, but you notice the bases are different, so I can't use the property I used in the properties of exponents, which are if the bases are the same, the exponents are the same. It's a one-to-one function. So I'm going to come along here and take the log of both sides, because it's a one-to-one function again. If I take the log, if the inputs are the same, then the log of the inputs have to be the same. The outputs have to be the same. But once I do this, I can use the power property to bring down those exponents. So I can rewrite this as 2x minus 5 times the log of 4.7 equals 4x plus 1 times the log of 3.5. But the cool thing, that's a number. I can plug that into my calculator. This is approximately 0.5441. Log of 4.7 is just a number. It's approximately 0.6721. If you're going to do this at this point, use your calculator, change those into decimals. Take at least 4 decimal places, because it will make a difference. So I'm just going to take this to 4 decimal places, and then I can just distribute, because I'm just taking now a number. I'm no longer a logarithmic equation, so that's sweet, short and sweet. I got awful decimals, but I can work with that. I get 1.3442x minus 3.3605 equals 2.1764x minus 0.5441. After this point, we're just solving a linear equation with, well, we got nasty decimals in there, but we can work with that. So this is a smaller x, so I'm going to get rid of this one. Subtract 1.3442x. And so I'll add the 0.57445441. I can't read my own writing. 5441. And I will end up with a negative 2.8168 equals 0.8322x. And I can just divide 0.8322. And I end up with x is approximately equal to a negative 3.3848. And again, to make sure this is the correct answer, I am going to go and plug that value back into x in this equation. So I'm going to have to do to check this, I'm going to have to do 4.7 raised to the 2 times negative 3.3848 minus 5 equals 3.5 raised to the 4 times negative 3.3848 minus 1. And if I do this, I'm going to end up with 1.23 times 10 to the negative 8 equals 1.23 times 10 to the negative 8, which checks. Both sides are equal. This is probably the messiest problem to work with of all these equations we're going to solve. Work through it carefully, and it should be fine. So let's look at some logarithm equations. These actually are going to look much nicer compared to that last problem I just did. If I have a logarithm equals a number, I'm going to do just like I did with its counterpoint. Get this problem, I just have a single log in it. Get it to a log equals a number, switch forms. So I'll add my 5. Get this to quit running around on me. 3 times the log of 7, log base 7 of 2x equals 6. I'll divide by 3. I'll get the log base 7 of 2x equals 2. And I'll take this over to exponential form. 7 squared equals 2x. And now we're a nice problem. 49 equals 2x. Divide by 2. And 24.5 equals x. Ta-da! And again, I can check this by plugging it into the problem here. And it's very important with logarithms that we do check this, because the logarithm does not have a domain of all real numbers. It has a limited domain, so we're going to find some problems sometime. Let's see what we mean. I'll leave this one for you to check. This checks pretty nicely. Let's go to the last problem. So here we have all sorts of logs all over the place. We're using the natural log on this one. Make it easy to write, because I'm going to be doing a ton of stuff. So I made it easy on myself. First thing I need to do if I want this to be a log equals a log is I got to combine these two logs together. So I'm going to take this up, use the power property, and then I'm going to use the product property to combine that to a single log. And I'm going to make this the natural log of 5 times 3 minus x squared equals the natural log of 125. And again, because this is a one-to-one function, logarithm is one-to-one, that means if the outputs are the same, the inputs have to be the same. For any output, there is only one input. So I can take this over and say, because those two logs are the same, 5 times 3 minus x squared has to equal 125. And that's not a bad equation to solve. So let's rewrite this. We have 5 times 3 minus x squared equals 125. I'll divide by 5 and get 3 minus x squared equals 25. Oh, that's so nice, isn't it? I'm going to take the square root of both sides. But again, when I undo a square with a square root, I get the absolute value. Or in other words, 3 minus x equals 5, or 3 minus x equals a negative 5. I'm going to solve this. Again, anytime I have a quadratic, I get two solutions. So to get these, I'll subtract my 3. Negative x equals 2. So I'll divide by negative 1. And I get x equals a negative 2. one answer. I'll do the same thing here. Subtract 3. Negative x equals a negative 8. Divide by negative 1. And I get x equals 8. So there's my two answers. So let's check these. Again, my original problem up here, natural log. Okay. Oh, let's come here for a check. If I take the natural log of 5 plus 2 times the natural log of 3 minus a negative 2, and this all I can plug straight into my calculator, I will get about 4.828, which is the same thing as the natural log of 125. So this checks. Negative 2 checks. I'm good with that. But when I come along and check the natural log of 5 plus 2 times the natural log of 3 minus 8, and I plug that into my calculator, I'm going to get 3 minus 8 is negative 5, and I'm taking the natural log of a negative 5. This is not in the domain. So negative 5 does not work. It is not a correct answer. This is something that we refer to as an extraneous answer. It's an extra answer that comes out of this process, because when we switched this over, said those inputs had to be equal right up here. We are ignoring the fact that the logarithm has a limited domain, and not every number that makes these two equal will work in here, because I cannot plug any number in for x, because right up here, when I'm squaring it, I'm okay, because I'm squaring it, I'm getting a positive number. If I plugged into this equation, I'd still be good with 8. But coming back to our original equation, I am not. So this one only has one answer. This is one of the reasons it is important you check your solutions. Make sure that no extraneous solutions pop up. But basically, when we solve these equations, it's going to be one of these 4 possibilities.